All right, what'd you come up with? Should be pretty quick. Bidentate, yeah. So coordination number of 6 means that there's 6 atoms bonded to that central cobalt atom. 4 of those are the nitrogen in ammonia, and then there's 2 spots that are left. So that means that the carbonate ion must bond through 2 atoms, and those 2 atoms are the oxygen atoms. Okay, bidentate. All right, so I mentioned last time that we will not be doing nomenclature, and that's still true, but the slides are still in here. So I just wanted to make sure that you understand, not tested on naming. There are a lot of rules, okay, for naming. I'm not going to go through all of these. There's a table in your textbook. Again, sorry about the, it's not so bad on the screen. There's some shading there on the table. Different ligands that you find commonly bound to metal ions, and their names and how they would be used in the name of that complex. So, for instance, water, we don't say it's we don't call it water, we call it aqua. Ammonia is amine with 2 M's. Carbon monoxide is carbonyl. Some of these you'll see again if you're taking organic chemistry. Hydroxide, hydroxo. So the names, usually the ending of the name gets changed a little bit just to make the name not on our list of a little better. They just roll off the tongue. For instance, pentaamine chlorocobalt 3 chloride is the name of this structure. Like I said, be thankful we were not having to do this. Whenever you see Roman numerals in parentheses, though, this is important. I think you probably saw this before. But the Roman numeral in parentheses refers to the oxidation state. So in this compound, cobalt is in the +3 oxidation state. We always name the cation first, so if we have something like this complex, the sodium tetrachlorooxymolybdate 4, the sodium ion gets named first. Okay, skip. So fun. All right, so let's get into some isomerization. There's a number of different forms of isomers. So this is a molecule, two or more molecules with the same composition of atoms, but in a different arrangement. And we're going to see structural isomers and stereoisomers. Okay, and our structural isomers are going to have different bonds. And our stereoisomers are going to have the same bonds, but a different arrangement. And that different arrangement refers to in 3D, in 3-dimensional space. So we're going to look at these models here a little bit. But let's go through and look at a few more definitions and explanations of what these different possible isomers are. So one type of structural isomer is a linkage isomer. It's a relatively rare type of isomer because there's only a few ligands that can form a linkage isomer. This is when a particular ligand is capable of forming a bond with a central atom in 2 different ways, or more than one way. So a couple of examples are the nitrite ion. I'm not going to draw Lewis dot structures, but it looks like this, nitrite. Okay. And then thiocyanate. I think we saw this last time. Has a triple bond, carbon-nitrogen triple bond, and a carbon-sulfur bond, single bond. And there's some, never mind, that's a different class. Okay. So structural isomers, because of the different atoms that are in these ligands that can bond, they can bond to the central metal atom in different ways. So here's 2 isomers, 2 structures for the isomers with the nitrite ligand. So we'll have our central metal atom. It looks like these are they're ammonia molecules. It's kind of hard not to use the naming structure, but anyway, these are NH3. This is the nitroisomer with our nitrogen and our oxygen atoms bonded that way. And this is the nitritoisomer where the oxygen is the atom that's bonded to the central metal atom. So again, the difference being that the central metal atom is bonded to a different atom on the ligand. Okay. The other thing that's kind of interesting here in the possible atoms that can be bonded to the central metal atom, usually those are going to be atoms that have a lone pair of electrons. Okay. There are other cases where the ion might be an ion with a negative charge, and that's going to form a bond. So we'll get to that in a little bit more as well. All right. So then I have coordination sphere isomers. So that's a different type of structural isomer. So what this is basically saying is that the central atom plus the things that are directly bonded to it, the stuff that's in the brackets, that's what's different. But there may be the same number and same type of atoms in general. So here are 3 different chromium compounds. There's 6 waters and 3 chlorides somehow arranged with these central chromium atoms. The chromium hexaaqua chloride, that's probably not the right way to name it, let's be honest. Once I found out we didn't have to name, I was like, okay, great. Just forget about it. Anyway, this compound is, I believe this is the one that's violet, yeah. So that is this. And the cool thing is that these compounds are different colors. And we're going to talk about why that happens. The one with 5 waters associated and 1 chloride associated directly with the central metal atom is sort of a gray-green color. And then the one with 4 waters associated and 2 chloride associated with the central metal atom is green, bright green. Okay, so can you see what's happening here with these structures and why they're different? The other thing to note is, I'm going to rewrite this one. So it's chromium, 5 water, chloride. So that's what's bonded to the chromium. 5 water molecules, 1 chloride. And there's Cl2 and a dot and H2O. So this H2O refers to the fact that this molecule is a hydrate. If we put this molecule in aqueous solution, these species are going to dissociate. Okay? Just like if it's a salt. There'll be an extra water floating around, a molar equivalent of water, and 2 molar equivalents of chloride. And that's different than for instance, the one with 4 water on the central metal and 2 water on the outside. Okay? This kind of goes back to how Werner came up with his coordination chemistry theory, the octahedral complex. We talked about adding silver ion to solution and determining the number of chlorides. It's the same sort of story here. Make sense? Okay, this one, different, that differs in what's in the brackets. So the brackets are what you want to pay attention to. All right, now the stereoisomers. The stereoisomers can be somewhat more tricky to identify. These have the same chemical bonds, but a different spatial arrangement, a different 3D arrangement. So the first type of stereoisomer that we're going to look at are the geometric isomers. So there's two types of geometric isomer. There's there'd be a cis isomer and a trans isomer. And I've got some examples of these. We don't need to worry about what the different colors represent, but we'll notice the yellow spheres versus the blue spheres. So there's no way that I could rotate these atoms so that they look the same. Okay, so that's what we're getting. That's the point we're making with the isomer. This is the trans isomer where the yellow are across from each other. This is the cis isomer where they're adjacent to each other. Okay. Yeah. So trans atoms of a type are opposite. Cis atoms are on the same side. It's sort of a little bit, that's not the greatest way to say that, I don't think. It applies better in a situation like this, where you have a carbon-carbon double bond, and we have atoms across from each other, so this would be trans, or we would have I got a little sloppy. Something like this, where they would be cis. Again, if you're taking organic chemistry, you're going to see a lot of cis and trans isomers across double bonds. One of the really interesting things that happens chemically is that the cis and trans isomers can behave very differently. This figure shows cisplatin. That's this one, and then the trans. I believe that's cisplatin, and then the trans isomer of that. It's not called transplatin. It doesn't have a real name because no one cares about it. Because the cisplatin isomer is really useful. It's used in chemotherapy, and it's active against many different types of cancer, including prostate cancer. The trans isomer is not active at all against cancer. So one of the reasons why drugs are so expensive is separating these isomers is really challenging. You need some specialized equipment to do that. And that's going to come up as well when we talk about stereoisomers, the expense of different drugs. You ever recently bought some Aleve or naproxen? It's more expensive than aspirin or acetaminophen or ibuprofen. And the reason being is that it has an isomer that is not active. And it's this type of optical isomer. There's one form of naproxen that is active and the other one isn't. And in some cases, it can be that there's one form that is active and one that is toxic. And I don't think naproxen is that case, but there are some drugs like that. So that's why those drugs can end up costing a lot of money. These types of isomers, these optical isomers, are really, really hard to separate from each other. You need specialized chromatography columns. You probably haven't done any of that, but and different things like that. I don't know how it's done on the huge industrial scale, actually, but it's probably something where the molecule has to interact in a special way, and the two different isomers interact differently, and so you can separate them out. Okay. Kind of getting ahead of myself. So we saw cis and trans. Okay, so optical isomers are molecules that have mirror images that can't be superimposed on each other. So your hands are great examples of chiral objects that can't be superimposed on each other. They're mirror images of each other. This does not count, right? So if I could switch my thumb over and all my fingers around, then they would be superimposed on each other. But this is just they don't match, right? Okay. There are a number of different enantiomers and ways of. You could have so many of these. This is a enantiomer of a set of enantiomers of cobalt with the ethylene diamine ligand. we're going to say that that is what these are. Again, ignoring the colors of the atoms. Usually in model kits, the colors of atoms represent certain things, but that's not going to be the case here. So let's pretend that this is our cobalt, and these are our ethylene diamines. And so you can see we have 3 different ethylene diamine ligands attached, again, bidentate. This is one of the isomers, the optical isomers, and this is its mirror image. Okay, see how that's the mirror image? Now there's no way that I could rotate this to make it so that it's superimposable. All right? They told me that might happen. Okay. They're held together with wax, apparently. Okay. I don't want to hold those too much more. You're welcome to take a look at these later on. But I have some other sets as well. So here's again some optical isomers, 2 bidentate ligands, and then 2 monodentate ligands. These are optical isomers. And again, there's no way I could rotate these to make them superimposable. Notice also with the green atoms that the green atoms are on the cis arrangement, so these are also cis-trans isomers. This would be the trans isomer. Okay, so these are isomers as well. All right. Yes?
So will this also apply to things like, it's like L and D DNA or something? Or
Yes.
Like, so you have 2, but one's not compatible with the other?
Right. Yeah, so we give these different enantiomers the term dextrorotatory or levorotatory, and it refers to the way that they rotate light. If you have polarized light, these different isomers will rotate that light in to a different direction, left or right. There are devices that are used to measure optical rotation. This is one of the ways that people will measure the amounts of sugars in different alcohols. Your glucose, dextrose, fructose, I believe those are all optical isomers. So you can measure the degree of rotation of the light using polarizing film and a polarimeter and figure out the composition. Slightly more complicated than that, but that's what this bottom figure here is trying to show you. This would be a solution containing a molecule or a complex that has some sort of optical activity. So it's a chiral molecule. Did I say chiral yet? Chiral refers to optically active. Okay, that's another word to be familiar with. And so what we'll see is if we polarize our light, so it has a certain orientation, certain polarization, if it shines through the optically active material, it can change that, rotate that light's polarization, and that can be detected. So yeah, it's kind of neat how that works. These isomers are pretty interesting chemically, like I said, about different drugs and things. Kind of challenging to figure out. Yeah?
How do you tell if that was rotated right or left, like in that example, that's 90 degrees?
Oh,
Like if it's
yeah.
vertically upwards and then it's like this, how do you know if it went this way or this way?
That's a good question. I don't know exactly. And there's probably, I don't think very many of them rotate 90. So it's going to be some fraction of that.
Alright, in any situation then, like even if it's like from here to here, I
Right.
don't know if it goes this way or if it's like that.
It's relative to a certain standard again. Yeah. So I was going to find a video that sort of showed this in action, but I couldn't find anything good. There was one that was a video that was okay, put out by the Royal Society of Chemistry. They looked at different sugars and how they rotate, and they had some standard, and then everything was rotated relative to that, either one direction or the other. But I've never actually, I don't think I've ever done one of these experiments, so I have very little experience with actually predicting which way it's going. Yeah. I feel like I must have done one of these, but I'm not recalling off the top of my head. It seems like you do these in organic, so let me know if you take organic and then if you do this. Okay. So your textbook has a nice flow chart for determining the type of isomer if you're given a molecule or a complex to look at. So the first question you would ask yourself is, are all the molecules the same on the two different, or do the molecules have the same atoms? So 2 different molecules, is everything the same? So isomers must have the same atoms. They're going to be arranged differently, possibly, or either through linkage, through structure, or in 3D space. If they don't have the same atoms, then they're not isomers, and you can just stop there. But if they do happen to have the same atoms, then we're going to consider whether the molecules have the same bonds. Okay? If they have different bonds, they're going to be some kind of structural isomer, either coordination sphere or linkage. If they do have the same bonds, they're going to be stereoisomers. Cis-trans isomers, those are our geometrical isomers, or the optical isomers, the chiral enantiomers. Okay, so let's say we have some sort of structural isomer. Again, our coordination sphere isomers are, you can identify these because you will have different species, if it's written out in formula, in brackets. If you're only shown the coordination sphere, you wouldn't be able to tell if you had, would you be able to tell? You might be able to tell. I'm trying to think of a problem. You might need to know all of the ions present, and if there is water that is associated with the hydrates. Okay. Linkage isomers are going to have the same species in brackets between each other, but they're going to be bonded differently. Okay, so that's the example with the thiocyanate and the nitrite types of isomers. Okay, if we have stereoisomers, our geometrical isomers are going to be cis or trans, which I think should be pretty clear. The optical, if the optical isomers are a little bit more challenging. So if you can make a mirror image, for instance, this molecule, if you could imagine its mirror image, might be a little bit challenging without having practiced this. But the mirror image would be superimposable on this molecule. So it's not a geometrical isomer, but not an optical isomer, but it is a geometrical isomer. Okay. So optical isomers, again, these are going to be either D, labeled as D or L, or R or S is also used, referring to the way that those isomers rotate light. R or S comes from German. I can't remember what the names are now. Anyone know German? Someone's wrong. I know someone. Okay, questions on this? All right. It'll be good to be able to predict the type of isomer or identify the types of isomers possible. Okay, it's going to be something you're going to want to be able to do. So let's take a look at this slightly blurry image, and figure out which of these does not have a geometric isomer. Again, the geometric being cis-trans. I'll put this up front for inspiration. So take a few minutes, talk with your neighbor. All right, what about molecule A? Does it have a geometric isomer? No. What geometry is that? Yeah, it's tetrahedral. Okay. No isomer. I want to go through all of these. No geometric isomer. And go through why it doesn't have a geometric isomer. Tetrahedral is kind of cool because when we draw it, it almost looks like this atom that's always pointing in the z direction has different arrangement. It looks like it has a larger bond angle between those that are on the bottom there, but it doesn't. So all of these are bond angle of 109.5. Even if we had two atoms of a particular type, we still wouldn't have a geometric isomer with tetrahedral. Okay. Does everyone see why that is? Okay. What about B? First, what's our geometry? Square planar. Okay, does this have a geometric isomer? Yes. So we could have, so this is our cis isomer, and we can make the trans isomer. Everyone see that? All right, what about these two octahedral complexes? So what about C? C is this, right? Yeah. So we know that if we take one of these yellow atoms and put it adjacent to the other, we would make the cis isomer. So there's our trans, that's what's shown in the figure, and then the cis. So it'll look something like this. And what about D? This one's a little harder to see. This does have an isomer. What you would end up doing is moving this to here. So you would have something like this. That one I find harder to see. I wish I had another yellow to replace this. But. Okay. Questions? Yes?
Qualify the cis or trans?
That's a good question. That is going to be cis, and we're looking relative to, we're only worried about this one.
Which one?
This bond, sorry, yeah, you can't tell what I'm doing there. Yeah, so that would, this one shown in the figure is the cis, this would be the trans. Okay, other questions? Okay. All right, so let's finally start to really get into the color of these compounds and some magnetism, which I time less interesting, but sure, why not? So color is going to depend not only on the metal center itself, but on the metal's oxidation state and on the ligands that are bonded to that central metal. Let's do a demo now. Let's just get. Okay, so based on just what I've said, so the color depends on the metal and the metal's oxidation state and the ligand. So what we're going to do is we are going to take cobalt chloride. That's the pink solution. That's this one. And nickel. It's a nickel sulfate. Okay, those are both soluble salts. And we're going to add ammonia to them. Okay, everything's aqueous. So I have graduated cylinders of ammonia. And what we're going to do is form a cobalt-2 complex with the ammonia, NH3,6. There are 2 chlorides there to balance it out. And with the nickel, we're going to form the nickel ammonium complex, and its counter ion is the sulfate ion. I want to point out one thing here. So when I wrote out these formulas, I put the Roman numeral 2 in parentheses for the cobalt, but I didn't do that for the nickel. The nickel has a 2+ oxidation state, but nickel only has 1 possible oxidation state. So just by convention, we don't include the Roman numeral on that one. The cobalt has different possible oxidation states, so that's why we include it there. Okay, so that's the first thing we're going to do. We're going to make some cobalt ammonia complex and some nickel ammonia complex. And we're going to look at the differences in color. And you might smell the ammonia. Let me take this off before I put these stupid Okay. We'll do the cobalt first. There we go. Ooh, really not a good look at it. That is not a good lid. That thing did not work. Okay, so according to Angie from Demo, it makes an ugly brown color. She's right. All right, so then let's do the nickel. Have any predictions? Purple. Makes a nice blue. Much prettier. All right, so we just have, the only thing different here essentially is the metal center. So you can see how that affects the color of these solutions. They're very drastically different. We will talk about what's happening with electrons and why that is the case, why we get these drastically different colors. But let's do one other thing. Let's take our cobalt, some of our cobalt solution, and put it in a flask that is charged with oxygen, filled with oxygen. I was told that I could either huff the oxygen or do an experiment, so I guess I'll go with the experiment. Okay, when we add the oxygen, we're going to produce what's happening? Okay, the stoichiometry is going to be wrong, but I just really want you to see that what we're doing is oxidizing the cobalt. NH36, Cl3. Okay, so the cobalt is going to be oxidized from cobalt 2 to cobalt 3 plus. Predictions? Yeah, it's getting darker, right? So just changing the oxidation state, going from cobalt 2 to cobalt 3, has a big effect on color. Cool, that was fun. Questions? That blue is really pretty. All right, set that over there. Okay, so let's see what happens. Well, okay, so let's first think about what it is that we're doing when we perceive color. So there's a couple ways that we see color in a complex. It's either an object will reflect that color of light, or the object will transmit all colors except the complementary color. So let's see what that means. So let's say you have an orange, and it's orange. So you perceive the orange color, and what's happening is only orange light is being reflected. Okay. The other way we could see color is by using a piece of orange film and looking through it. Again, we'll perceive the color orange, but what's happening, if you'll notice the difference in this area of our spectrum versus here, right? The blue color is being absorbed by the orange film, and I'm sure you've learned this at least one time in your life. Orange and blue are complementary colors. So the blue light's being absorbed by the film and we're perceiving the orange color. Color wheel actually does come in useful in this class. So you know your complementary colors, it might come up. All right, but what does that mean in terms of an absorption spectrum? Have you guys done a Beer's Law type experiment in lab? Okay, good. So you know that when you collect an absorbance spectrum, you are plotting on our y-axis absorbance versus wavelength on our x-axis. This is the absorption spectrum for this solution, which appears purple. And what we see happening is that, let's see, some of the blue, some of the green, and yellow are being absorbed by the compound. And that means that the red area and blue area of the visible spectrum are being passed through the solution. And that combines to make the solution look purple. Okay. I haven't got to any of the electronics of why that happens, but let's look a little bit about some background on magnetism. So magnetism occurs because compounds contain electrons which have spin and cause a magnetic moment. We have some general forms of magnetism. We have diamagnetic solids, which have electrons which are spin paired, and their dipole moments cancel out. And these types of things are repelled from a magnetic field. key thing here, spin paired. That's going to come back, all right? So spin paired, repel from the magnetic field. Some good examples of these types of compounds are copper, silver, gold. Okay. If a substance has unpaired electrons, it's referred to as paramagnetic. And in this particular instance, the atoms don't affect each other. These atoms can be, or substances can be attracted to a magnetic field. All right. Good examples here are magnesium, lithium, molybdenum. They're not great examples because how many of you have ever held magnesium or lithium or molybdenum? No. Okay, whatever. Anyway, there are 3 other types of magnetism. Those are ferromagnetic, antiferromagnetic, and ferrimagnetic. So ferromagnetic substances are where the spins are aligned parallel to each other. So these spheres are going to represent electrons and the orientation of the spin. Ferromagnetic substances can retain a magnetic field, and so this is something like iron or nickel or cobalt. Antiferromagnetic is when the spins are aligned but in opposite directions and they cancel each other out. So the spin might be up and then down for another unpaired electron. So these spins are affecting each other. Something that is an antiferromagnetic substance that you may have seen or played with before is hematite. It's a mineral. It has the formula Fe2O3. And then ferrimagnetic with the I instead of ferro. These occur in ionic substances. So again, we have spins that are opposite in sign. They're affecting each other, but the magnitude of the spin is different. And that's because the spins are coming from different substances. A good example here is magnetite, which has the formula Fe3O4. So a lot of our transition metal complexes exhibit paramagnetism, so they have unpaired electrons. And many of them are diamagnetic, but we can determine experimentally the number of unpaired electrons. So an experiment was run on these 2 different cobalt compounds, and it was found that the cobalt cyano complex, this first one here, had no unpaired electrons. And then experimentally it was found that the cobalt fluoro compound has 4 unpaired electrons per metal ion. Both of these cobalt metal centers have the argon 3d6 electron configuration. Okay, so there's 6d electrons, but there will be significant differences in the arrangement of these electrons because some of them in the cobalt cyano complex are unpaired, but there are only 4 unpaired on the fluoro compound. So why does that happen? Why do these different ligands cause that effect to happen? We're going to need a bonding theory in order to be able to explain that, and that's